Awesome. Volume is a little bit too high. Cool. And I think the screen is already on, everybody, and also welcome to the last lecture of this week, right? And also this is the second last week. So we don't have too many here. I think maybe others are still coming. I hope these are not the people who are left or remaining from the course. I had the impression that we had more. Because I think at the moment, at least for people who are here, I hope you are at a already quite comfortable phase. If you imagine the diagram that I asked you or showed you at our first lecture about your, let's say, emotion versus the knowledge or versus the time. And I hope everybody is now at really a rather climbing phase towards the final stable end. And probably you are also at the rather stable kind of condition. That would be awesome. If you're still reaching there, no problem, continue. And because the next 2 lectures or even next 3 lectures really is trying to get everybody more familiar with what we have been teaching you and what you have been still learning and how to apply them into different scenarios. Let's just move to the diagram that I try to show you almost every lecture now. It's becoming really, really frequent. Maybe you don't see it in the previous weeks, but now we're really just talking about this almost every lecture. Because now every lecture is more or less about a kind of small addition to this puzzle pieces, let's say, and you're also applying what you learned before and to basically learn the new stuff. So this is really getting a very comfortable phase for you because you have been through the most theoretical and the fundamental part. Let's just try to get it started, and I will make it even more specific this time because now it's not really just about previously, it's really about the lecture flow. So we started from, let's say, structure. Yes, so I'm speaking about this tetrahedral here, and we started from structure. Now, if you just recall what you have learned from lecture 1, yeah, we were really speaking about electronic and atomic structure. And in lecture 2, so the second lecture in the first week, we spoken about crystal structure. You remember FCC, BCC, but of course, what's beyond the crystal structure was the defects. Yeah, maybe you remember the point defects, line defects, and all this stuff. And then you learn dislocations, and maybe one of the most important concepts for you from this course. And afterwards, actually, we did some jumping, but hopefully you just recall last week, we really learned about another kind of structure thing, which is called phases. I mean, you learned it, but we gave you a proper definition until last week, I guess. Now you learned what are phases and how to define a phase and what kind of phase is giving what kind of mechanical properties or features. And after that, so you see from the structure point of view, we're zooming out. So we really started from, let's say, nanometer level, and then we went to micrometer, and somehow, let's say, sub-millimeter level, if we speak about microstructure or phases. And what we learned on the structure point of view is kind of meant to make connection between the structure and the properties. So we learned about properties starting from the second week, maybe you remember. And we started with elasticity in the lecture 3, and also plasticity 3 and 4, and also hardness. Then we focus a lot on failure. So lecture 5 and 6 on failure. And after failure, so we didn't specify, but actually during these lectures, we also moved from properties to performance, right? If you remember, so performance is nothing but integration of a bunch of properties. And at the same time, you zoom out and you just look at a, let's say, product or structure instead of, material from a rather small scale. And this week, or let's say starting from last week, actually, we started to look at the, let's say, processes. Yeah, so these 2 points, you remember we were talking about structure property relationship, and this is the key for material science. And when we just move to performance and processes, we're really moving into the canon of material engineering. And for the processes, we gave you some prerequisites to be able to learn processes. And these are diffusion and phase diagram and phase transformation. And that's what you learned last week, basically. And finally, this week, we learned some detailed processes just yesterday. So I hope you enjoyed all this kind of casting technology, forming technology, and most importantly, the heat treatment. So how you cook your material to make it behave soft, make it behave hard, ductile, brittle, all these features. And all these processes will finally decide your structure. And so I would say at this moment, guys, you really got this kind of tetrahedral connected. Maybe you don't realize yet, but you're gradually becoming an expert of material science and engineering. So if you just recall what you had in your mind, basically 5 weeks ago, when you just came to this lecture, I think you know the world, or you know anything around you much, much better than 5 weeks ago. Yeah, I hope you had this impression, and you should be proud of yourself if you have this impression. And at the moment, you see the tetrahedral are more or less connected. Of course, we left a few or 2 bars out because they're kind of not directly connected. Well, you could also claim they're directly connected, but they're always connected via another end. For example, we know structure is decisive for performance. Why it is? Because performance basically integration or kind of average value of different properties. So that's why it's always connected via this kind of tetrahedral, or not kind of directly this link. So we don't talk about that, but if you have the data, of course, you could build up the connection. So I would like kind of remind you about our learning, let's say, mechanism or learning methodology when we just talk about all these connections, or we talk about one dot itself, is we always go, let's say, with the characterization, so with experimental observation. Yeah, maybe you find out this is the methodology we're doing. So first we try to observe what is there, and then we try to formulate a theory. So the theory could be qualitative, could be quantitative. Yeah, so qualitative basically given by, let's say, definition, explanation, and so on. And for quantitative, basically we're relying on equations, try to explain things. And of course, the last item is modeling, because equations sometimes cannot give you all the details. For example, we learned about diffusion, and you learn about all the Fick's laws, but if they're expressed into a differential equation, and you could only resolve that when you have ideal case, when you have really regular geometries, like a cube or rectangular or round shape and so on. If we talk about the irregular geometries in reality, something with defects, something with a notch, you really need modeling. So you really need FEM modeling or any kind of modeling to make everything quantitative and accessible. So this is our kind of basic methodology. I hope you could, let's say, learn this kind of methodology for your learning, because this is not just about material science and engineering. Maybe it's about, in general, how to learn the learning methods. Yeah. So we always gave you knowledge for every lecture, but probably you don't learn how to learn. Yeah, that's a subject maybe we should think about in the future. But at least in this lecture, we try to give you kind of, the methodology or philosophy to help you learn how to learn. Yeah. So these are the methodology we're trying to kind of carry out for the lecture. All right. So as you can see, everything's complete, and it seems like you're done, guys. Yeah. You could enjoy the rest of the week and get yourself ready and prepare the exam, and we're done, and go for a nice Christmas. Just two more things, actually, not too much, only two more things. So today we're going to talk about one of them, and next week we're going to talk about the other, and then you're fully done. Yeah. The first thing we're going to talk about is rather falling into this bubble, so the structure bubble. Maybe you kind of remember we started the lecture with atomic structure, and we started the lecture by showing you what are the material types. Yeah, we spoke about that at the beginning very often. So we always spoke with metals, ceramics, polymers, maybe remember composites sometimes as well. And we even spoke quite a little bit detail when we just were studying, electronic structure and atomic structure over there. But then, let's say, starting from the lecture number 2, we really focused on metals, yeah, and so on. So we kind of started here with a general introduction, and then we basically led you through this kind of connection of the tetrahedral via metals, yeah. This is not a coincidence, and this is done on purpose, because we want to show you these connections, so you'll be able to think the big picture always when you talk about materials. And we try to demonstrate all this via metals. The reasons are two. The first one is metals are the most frequently used, let's say, engineering materials, yeah, especially when we talk about mechanical engineering, right? Even for very much, let's say, civil engineering as well. Yeah. And the second reason is that metal is rather, let's say, in the middle, not that complicated, not that simple. Yeah. So you will see for, let's say, ceramics, there are things a little bit complicated. And for polymers, they're a little bit, pretty simple in a way. And metal is a complex that shows very good knowledge for you to learn. And with this knowledge, you will be able to, let's say, learn a little bit of complicated things, and also to learn the rather less complicated things. And that's why, so for today, we're going to first show you what is going on with the ceramic, in terms of all their, let's say, structure level properties, structure level characteristics, and a little bit on their property, not that in detail, but we're going to focus on the crystal structure of ceramics. We're going to show you how the defects are looking like in ceramics, and what is the phase diagram for ceramics, and so on, and how this kind of properties are going to detect the let's say, plastic behavior of certain properties of ceramics. And this is for today's lecture. So basically, you will see many kind of concepts that you have learned coming back to you, and you will learn a lot of analogy. At the same time, you will also learn something new. Okay, so that brings us to the objectives of today's lecture. So you have basically 5 items that you are not familiar at the moment. So you even don't know the names of them, most likely. But I can guarantee after 1.5 hours, you will know them pretty well. So the first one is you will be able to name the types of ceramics, and also describe their basic applications. So I think different from metals, for ceramics is a term you probably know, but you don't really know exactly. Yeah. So we're going to show you. And the second objective is you'll be able to sketch or describe the unit cells of a class of ceramics. So for example, sodium chloride, cesium chloride, zinc blende, and diamond, and so on. So you will be able to know even the atomic structure of graphite and also silica glass. So you see a lot of names, a lot of kind of new materials. You'll be able to get a sense of them. And even you're able to tell them what is their, let's say, atomic and the crystal structures. And the third point, you will be able to do something a little bit different or more complicated than the metals, because for, let's say, ceramics, it's not just one type of atoms matter. It's actually usually two, right? That's why we need to learn something called chemical formula. So you'll be able to kind of know what is the connection between the crystal structure and the chemical formula. So we don't speak about this at all when we were speaking about metals, but this is something addition for the ceramics. So basically, this is still about the crystal structures. It's just a kind of something additional for you to learn about ceramics. And then we move to defects. Yeah, so you're going to learn what are the point defects for ceramics. Yeah, it's very similar to metals. And finally, we're going to make certain connection from the structures that we have learned about ceramics to their properties. The property is mainly focusing on mechanical and also a little bit on thermal. All right, so that's the kind of learning objectives. Now let's move to the first topic. It's about types of ceramics and also their applications. First of all, I try to give you a definition about ceramic. So this is a rather long one, so I'm going to read with you. So a ceramic is any of the various hard, brittle, heat-resistant, and corrosion-resistant. So 4 kind of adjectives: hard, brittle, heat-resistant, and corrosion-resistant. All right, and this 4 types of materials made by shaping and then firing a non-metallic mineral, such as clay and high temperature. Let's just forget about the such as first, and let's just digest a little bit about this definition. So first of all, we're talking about 4 characteristics of this material, and this is describing the properties of ceramics already. So usually they are hard, brittle, heat resistant, and corrosion resistant. And how do you make it? And this is property, and this is something about process. Yeah, this is made by shaping and then firing of what? Of a non-metallic mineral. So you see, the key word here is non-metallic mineral. That's why they are ceramics. They're not metal. Yeah, because if you just look at here, this property definition or this property description and also the process description, well, they're not exactly the same as metals, but very much similar, right? But the key word is here, it's a non-metallic mineral. So hopefully now you get a sense of ceramic. Maybe before I gave you this definition, what you think about ceramic is mainly clay, right? Because they're made of the most often see ceramics in your life is the kitchenware. So whiteware, all this stuff. And maybe the most seen, at least that was for my generation, maybe it's different for you guys. The most seen when you think about a ceramic is from the movie called Ghost. Maybe some of you know if you watched with your parents one day or so, because that was exactly explaining you this part. So what is about shaping and then firing? Because maybe you remember the scene is shaping. You're shaping a kind of kitchenware, and afterwards you're going to put that into fire, and then you go through a high temperature and solidify, and finally you get your ceramic. That is exactly related to the kind of the word ceramic. If you know Greek or maybe ancient Greek, I'm not sure. Ceramic means actually literally from Greek means burned stuff. So some stuff that was burned to become. Yeah. I think that's all enough about ceramics. Hopefully you now get a sense about it. Yeah. The key word is something non-metallic, and it has 4 characteristics in terms of properties, and they're usually processed via shaping first and then firing second. Now, all right, so now let's move to a few really kind of types of ceramics. So you have many. They're not characterized here via, let's say, the kind of composition. Like when we talk about metals, we always go with iron alloys, steels, basically, and aluminum alloys, and so on. So for ceramics, we kind of characterize them via applications. And the first thing you probably know, you probably don't, of ceramics is glasses. Yeah. If you don't realize why glasses are ceramics, or basically why glasses are produced via this process, you will know in about 30 minutes or so. Just to tell you, glasses are a kind of material that is really born from this process, and this is one of the important ceramic products. And I don't need to name the really typical applications about glasses. So they're optical, and you can use them into many kind of applications almost everywhere. So kitchenware, house food, containers, and so on. And the second one, yeah, maybe I mentioned already, is plain products. Yeah, that's the typical application of ceramics as well. So wideware, structural materials as well. You need to use some clay products. And the third one is most likely less often seen for you. It's refractories, because they're kind of a basic composition when you just look at furnaces, especially for the kind of industry application furnaces. You need to have really high temperature material to build that furnaces, and these brakes are usually made by ceramics. But if you happen to visit a rather ancient pizza oven, yeah, or pizza restaurant, then they are probably doing their pizza not by the modern ovens, but the rather ancient ones. You see the oven is built by all this kind of brakes. Yeah. And the fourth one is very connected to finally our material science engineering. These are the sandpapers basically used for cutting and polishing. So this type of application for ceramics is called abrasives. Why we're using that, we probably didn't introduce you very at the beginning, but we need to, for material science engineering, always cut stuff and observe stuff with a microscope, right? You cannot observe stuff via microscope if you don't polish the surface. So you have to really get your surface so smooth and so clean to be able to really reflect the electrons and see their microstructures. Yeah, you can see those microstructures in our classes. And they were always processed by, abrasives. If you are interested in this, how to process, Rongfei is a very good candidate to tell you how to do all this preparation of your samples. And you will be able to see what are their phases, what are the crystal structures, and etc. Yeah. And the other fifth one is something common to see actually, as cement. They're mainly used for structural applications. And then we also have biomaterials. Maybe something like implants, probably not by yourself, but probably by some elder people or so, or someone who had accidents or so. And that is made by ceramic, because ceramic has a very good feature, and that is usually inner to the environment, like heat resistance and corrosion resistance, right? And the second last is carbon. Maybe you don't feel like carbon belongs to ceramics, but yes, they do. And especially two types of specific carbons. We will show you what they are. So if you just think about the coal, maybe that's not exactly in the field of ceramics. And the last one is rather general, so advanced ceramics. They will go to, you know, etchings, robots, and so on. And we will not talk about this at this lecture. All right, so that's the general opinion about the ceramics. I think everybody now feel like, oh, I know the material, right? And let's give you something more specific to our lecture. So you know very common applications, as I already talked to you. And specific to our lecture, the first applications I want to give you is the kind of dye blends. Yeah, this is something you learned yesterday, I guess, right? So when we were talking about processes, exactly yesterday. So this is a process you know, probably. Yeah, this is basically drawing. You remember the process? We need to, if we want to just to reduce our cross-section of the material or tailor the shape of the material, we need to apply this kind of forming technology. So we're going to draw that. We were focusing mainly on workpiece. So this metal here is called workpiece. And we didn't tell you about these two things. So these are called dies. And basically they are fixed over there and they're kind of getting a shape that you want. For example, these are the dies. So here is hollow, right? Your material is going through that and becoming thinner. If you want your material even smaller, and you go with a smaller one. And these dies, we didn't specify, but these dies are usually made via, not directly via ceramics, but indirectly. I will tell you why. This dies, the substrate, so the matrix of it is usually a hard metal. It could be steel, but usually we go it with tungsten carbide. Yeah, so tungsten is a material you probably know. Hard metal, very hard. Hardness over 1,000 Brinell. And but it's still not hard enough. If you just do it, you know, this drawing process time and time again, and you don't want your dye kind of worn out. You want the dye lasting as long as possible. Otherwise, you're going to create that dye again. You have to stop the process, which is not good. And that's why we try to create the dye as hard as possible. And this is application of ceramics. To be more specific, it's application of a diamond. Not diamond you see, when you have a marriage or so. This is because that diamond, maybe you know it, maybe not. The diamond of that is basically a single crystal. That's why it's expensive. And maybe you could also think about the diamond itself is costly, but what is more costly is the process to cut it. You have to think about, if the diamond is the hardest material in the world, so how do you cut it? That's a nice question you need to think about. We'll probably tell you in the next slide already. The kind of diamond we're using here is same, but we're basically using polycrystalline diamond, so that they're way cheaper already. And you basically kind of deposit this kind of polycrystalline diamond. So here I give you a number 4 micrometer, thickness 4 micrometer. If you don't have any imagination about what is 4 micrometer, I could tell you your hair. The diameter of your single hair is about 50 micrometer. So the layer of this diamond is about 1/10 of the diameter of your hair. So very, very thin, but it's already very helpful. And this kind of a polycrystal diamond will be deposited into this tungsten carbide substrate, and that will really improve the life of your dies significantly. Yeah, and the second feature about this kind of diamond is they will give you rather a uniform hardness of all directions to reduce wear. Okay, so that was the first application, and the second one that is related to our business here is cutting tools. Yeah, I already told you. We need to observe our materials, so we need to produce this kind of abrasives and cutting tools to get our materials prepared, and this is for this cutting tools. So maybe you can see I will go actually backwards for this grinding glass, tungsten, and carbide ceramics. Yeah, so basically these are the thing that you see. So the single crystal diamond, which are here, and the polycrystal diamond, which are here. Yeah, and the second application for the cutting tool is to cut, let's say, maybe something that could draw your attention is cutting silicon wafers. This is very important if you're doing something in the chip industry, very critical. And the last one is rather massive, is about oil drilling. So this part is also made ceramic because it's hard enough. All right. And that's enough for the second application. So by the way, here is explaining how do we basically manufacture diamonds, because you have to rely on their cleavage planes. So you try to trigger a cleavage fracture of your diamond. Yeah, that's why when you just see the polycrystal diamond or you see a single crystal diamond, you see they're really into all these facets here. Yeah, it's not like a round shape, a smooth one, but you see all these facets. Actually, these plates are crystallography plates, and because you can only get them broken when they have some certain cleavage fracture. Remember that these materials are hard but brittle. Yeah, when you just use a right kind of force in the right direction, you will trigger their cleavage fracture, and they're going to be kind of broken on a certain cleavage plane, which is a certain crystallography plane, and then you get manufacture of all this kind of diamonds. All right, that's enough for applications, and let's move to the structure point. So we're gonna start with very kind of recap about the atomic bonding or atomic structure of ceramics, and then we move to the crystal structures and defects. So actually there's not too much to talk about. What I need to remind you is for ceramics, we're talking about atomic bondings with, maybe you still remember from the day one lecture, ionic and covalent. So for metal, we didn't really emphasize quite much or even not at all about their atomic bonding, because you remember their metallic bonding. Metallic bonding has a unique feature, that the electrons are basically floating into a electronic sea, and there's no direction kind of developed between the electrons and the atoms of your metals. But what is specific for ceramics is we will develop all this very directional ionic or covalent bonds, and this will be the decisive factor for the crystal structure of ceramics. And you will just know in a few seconds. Just to remind you, what kind of combination will develop ionic, what combination will develop covalent, maybe remember. If we just speak about something like calcium fluoride, these two guys, when they have very distinct electron activity, maybe remember, right? We will have the kind of tendency to develop the ionic atomic bonding. And if we speak about something with very similar electron activity, here I'm showing you silicon carbide, so these are almost identical, and they will tend to develop covalent bond. If you remember the formula, you don't have to remember, you should remember there is a formula for you to calculate what is the tendency or what is the fraction of these two types of bonding when you have a ceramic structure. All right. Okay, good. That's enough for you to recall. For ceramics, we're going to have really something directional about the atomic bonding. Because this is decisive for a crystal structure. Here I'm giving you an example about oxidized structures. Actually, they could be applied to fluoride and all these other ceramics as well. And the first point is for the oxide structure, the oxygen anions are much larger than metal cations. Maybe you could imagine, or maybe you're wondering, no way. Yeah. If we talk about iron oxide, and I have the iron atom number with 56, and the kind of oxide is much smaller, I should have a very big metal cations than the oxygen anions, right? Let me see if someone is here. Okay, good. I will tell you the answer right away, because the metal cations, they're bigger. They have a bigger atomic number, but you remember the size of your atomic structure is really decided by the electrons. And when the metal cations kind of lose their electrons, actually they become much smaller. So when they from a atom becomes a ions, and their size becomes much smaller. That's why you always have a bigger anions than the metal cations. You will see some numbers right away. So this is the first feature, and the second is our oxygen anions kind of tend to always formulate a FCC structure. So this is something you should feel familiar about, because when we talk about metals, our atoms naturally will go with the closed packing, or rather closed packing. So FCC is CP. They provide the closed packing, and followed by BCC and Q. So the oxygen anions, they will just form a FCC structure, no doubt about it, because they will formulate via the closed packing. That comes to the third point, which is the finally decisive one. So when the kind of oxygen anions develop a FCC structure, the question is basically where the kind of metal cations will fit in. Yeah, so because they're much smaller, and they need to sit there to make sure the whole structure is stable, and the whole structure is neutral. We have to decide where they're going to sit, where they're going to fit in, and the conclusion or the feature is they will basically fit into the interstitial sites among the oxygen ions. Yeah, you probably remember what are the interstitial sites. If you don't, we're going to just show you right away. So remember, these are the three features about the ceramic crystal structure. And basically now we're going to learn, when we have these features, these three observations in mind, what kind of crystal structures the ceramics will develop. Yeah, there are two rules the ceramics crystal structures should follow. The first one is that the relative size of ions. Maybe this is rather abstract, but the follow-up kind of definition will give you a more clear kind of concept. The concept is the crystal structure that will be stable for the ceramic is really trying to maximize the number of oppositely charged ions when they have neighbors. So just to put it into a little bit graphs to show you what does that mean. So if you just look at these two figures on the right-hand side, you see for this middle one, we have 4, let's say, anions touching each other. So they are FCC. If you just extend it, or at the moment they're not FCC. At the moment they're kind of in the cubic structure. Let's say we don't mind about that. And they're touching each other, and that's okay. Yeah. And most important thing is your cation, metal cations here, is really touching all the other, let's say, anions at the same time. Yeah, because the key factor to make sure the structure is stable is that they neighbor with opposite charged ions should be maximized. Yeah, so here my cations are touching 4 anions. That is good, because now I'm maximizing this number, maximizing this neighbors with oppositely charged ions. The third one looks a little bit less stable because all the kind of anions are not touching each other. So they don't have neighbors in a way. They're only having a neighbor, which is this cation. And you should know this is also stable, because what matters is not absolute numbers that are becoming neighbors. Actually, it is the neighbors that the kind of ions have opposite charge. Yeah, so this is clear for you, I hope. And now if we just look back to the first one, so you can see here the ions, the anions, they're having quite good neighbors. Yeah, for example, this guy, if you just imagine, has 4. But that doesn't matter because it has no cations as their neighbor. Yeah, that's why it's not stable. And this cation is only touching 1 at this moment. Yeah, it should at least touch 2, right? Because it's so small. You cannot touch 4 at the same time, but it can definitely touch 2. That's why it is not stable, because it's not maximizing the number of oppositely charged ions neighbors. I hope that is clear. So this is let's say, the first rule to construct a stable crystal structure of ceramics. Yeah, and the second rule is rather, let's say, easy to understand, and you learn all this from high school. And for ceramics, we have to make sure our material is maintenance of the charge neutrality. Yeah, so we cannot have the materials not neutral afterwards, basically. And for example, here when we speak about the calcium fluoride, it has to be 2 fluoride elements is corresponding to 1 calcium element. Yeah, and this is something rather simple, and we will just try to elaborate to you a little bit later. If you just combine these 2 features at the same time, you will get the sense of it, because the first feature is deciding basically what kind of structures you will have. Yeah, so because they will decide how your atoms are going to be, or your ions will be situated. And the second one will basically decide the number. Yeah, decide the number of cations will be sitting. Yeah, to be more specific, if you just recall what I explained at the beginning or at the last line, because our anions will basically structured into a FCC crystal structure. That is clear. So for anions, the crystal structure is rather clear. But the situation is basically to learn where the cations will sit into this FCC. They will sit into the interstitial sites, but we need to know where, because there are many interstitial sites. And the second rule basically is going to decide how many of these cations will sit into a unit cell. Yeah, because we have to follow the kind of neutrality rule. Okay, so hope that is clear. So the first one is deciding where they're going to sit, the cations are going to sit. And the second one is going to decide how many cations are going to sit into the interstitial sites. So this one is basically telling you where the cations are going to sit into the, let's say, FCC structures of the anions. So what designed that? So maybe from the rule, the factor 1 or rule of 1, you have already have kind of sense of it. The decisive factor is basically the size. Yeah. So if the cations are really small, yeah, it will not allow it to touch too many anions at the same time. When it's big, you could develop a certain relationship, right? So here I'm giving you the theory, basically, how to decide that. The idea or the measure to decide this is done by ionic ready. So the ion ready basically is a ratio between the radius of your cations over the radius of your anions. So this is rather simple, I guess. And a other concept to be clear with is the coordination number. So this coordination number is in line with the coordination number we defined when we speak about the FCC BCC structure, maybe remember. But now we have to be a little bit more precise about it, because here we're talking about the two kind of atoms, and the coordination number here is meaning one, let's say, cations is in touch with how many anions. So 1 into 2, meaning one cation is in touch with 2 anions. So it has 2 neighbors. So this is the definition about the coordination number. Let's start with this table here. So we said the decisive factor is this ionic ready. And as I said, if we have a rather small number here, basically the radius of the cation is so small, below 0.155, what you could afford is only 2. So you cannot maximize the coordination number more than 2, because it's too small and it can only touch 2 anions. Very easy to understand. And the structure that we're going to form is going to be a linear structure, right? Everybody follows. And the second structure is when your radius of the cations becomes a little bit larger. Yeah, so you can see here. And it's between 0.155 and 0.225. And the cation is becoming large enough to be able to touch 3 anions at the same time, right? And in this way, you're going to formulate a triangular structure. What is common about the first and second is they're basically 2D structures. So either coordination of 2 or 3 basically going to give you a 2D materials. So we're not really focusing on that. They're rather rare in the reality. What is important is one, the ionic ready is larger. So between 0.2 and 0.4, and this is giving a large enough, let's say, cation to be in touch with 4 anions. And we're going to formulate a tetrahedral structure. So everybody now is very familiar with this structure, yeah, because you look at almost every week or even twice a week, yeah. And so basically we have 4 anions in this 4 kind of vertices, and right in the middle. So if you just look at transparently on top, you see right in the middle, there's sitting a cute cation over there. It is in touch of this 4 anions. One example here, so here I can give you an engineering example already, is this zinc blend. You see they kind of anions, they're in a perfect FCC structure. Yeah, you recognize that, right? The blue one, the green one. And the cations are basically sitting into the interstitial places. So as they are so small, they could really sit so many different places. And we need to decide where they're going to sit. So they're going to sit right here. Because first of all, you will find this kind of tetrahedral from your FCC. Yeah, maybe you see it here. So this tetrahedral is composed of one corner atom or one corner anion with 3 phase anions. Yeah, I hope you get it. So this is a phase atom, this is another phase atom, this is the bottom phase atom. So with this 3 atoms plus this corner one, you kind of construct a nice tetrahedral, and this cation is going to basically sit right here. If you just look at the whole FCC cubic, you see you're going to sit 4 of these cations. What decides that? Yeah, think about it. What decides that? Why they're just sitting 4, not many? Actually, you have many positions of this kind of cation, of this kind of tetrahedral. Yeah, remember the second rule. We will talk about that in a second. And let's say if we have an even bigger ionic ready, so it becomes between 0.4 and 0.7, and that is making sure your cation could be in touch with even 6 anions at the same time. And so the coordination number is 6, and the structure we're going to form is a octahedral. So octahedral is something we didn't talk about, but I think everybody knows it. Yeah, so we have basically 6 atoms. So here is a top view. So we have 4 in the middle plane, 1 on top and 1 on the bottom. And the cation is basically at the center of it. A best view of this is via a kind of FCC cubic. So here we're giving you the famous sodium chloride. Yeah, everybody's familiar with that. You see the chloride anions, they're forming again the FCC structure. So the green ones, you can recognize that. And the sodium cations will decide where to sit. Yeah. So where they're going to sit, they will be able to sit right. So you see there are odd edges in the middle of every edge here, and even the completely body center of this FCC cube. Yeah, this is the best one for you to visualize this octahedral kind of structure, because if you just look at this atom right here, you see on this plane we have 4 anions, and on top we have 1, on the bottom we have 1. So this 6 anions are constructing exactly a very cute octahedral. And for the other kind of cations, you could imagine the same, but you have to imagine the others, not just the one cube unit cell, but the neighbors, right? So once again, this kind of ionic ready decide where the cations are going to sit, but what decides how many? So why they have to go through all the edges, and even 1 in the center, is something for you to think about. I think you can definitely figure it through. Yeah. So the first one is decided by their formula, maybe remember, and then you should think about what are the equivalent number of your anions and of your cations in a unit cell. All right, finally, if your ionic ready really becoming so big, it is between 0.7 to 1. So think about what 1 means. 1 means we are getting equal size of the cation and anions. It's more or less a metal, right? And with this kind of size, the octahedral cannot be stable anymore, because it's becoming too big of the cations to get into a interstitial like there. And finally, we develop a cubic structure. So looking like that. So here you have to imagine so example is given by cesium chloride, and the chloride anions are not following a FCC structure anymore, because we cannot afford it, as the cations are too big already. And basically it is a simple cube, and the cations are sitting at the body center. So this whole structure actually is forming a BCC structure. Maybe you see it, right? So if you just imagine this is the same atom. As you can see here, this table is basically giving you what is a crystal structure will be more or less looking like. Okay. And I think this is also the good time for us to take a pause here. And let's just take a few minutes for break. And let's meet everyone again at 11:15. All right. And now let's just continue with today's lecture. We've just gone through actually maybe the most important concept for today. You also probably felt the same. This is directly something completely new for you. So I hope everybody got it. So the concept of ionic ready and also how they decide the crystal structure when we talk about ceramics. All right, so that's the first most important rule. And as I said, that who gives the crystal structure. So here I gave you a little bit details about how the numbers are calculated. And I think everybody has a sense of it, right? For example, when we talk about minimum, let's say, kind of ionic ready, so the kata-ana radius ratio, why it is, for example, 0.4 something, when we're gonna have a kind of octahedral site right here with a Cornish number of 6. Actually, the principle is rather simple. The minimum number is decided by actually the size, right? So first of all, minimum is decided when you have your, let's say, anions are touching with each other. Because if they're not touching with each other, basically will allow or tolerate a rather bigger, let's say, cation. So if they're touching each other, we're having the minimum case, right? That is first rule. So that gives us the first equation that the A here is basically equal to 2 times the radius of anions. That's clear. And the second equation, or the decisive one, is basically telling us if the cation should be kind of giving a stable crystal structure, and the size of the cation should be fulfilling this equation. So basically, the 2 times radius of anion plus 2 times radius of cation should be equal to square root 2 times A. Everybody understands that, right? If it is smaller than this, so we'll not be able to formulate a stable structure with octahedral kind of structure. All right, if we just simply rearrange this equation and do some calculation, you will see that will lead to a ratio of 0.414. And that's exactly how we calculate the minimal ionic ready. All right, so that's a little bit demonstration about these numbers and how do we use it. So this is how do we use it. So when you have a, let's say, a ceramic, here I'm showing you iron oxide, and you probably get the size of the cation and anions of those 2 atoms, and you will be wondering, okay, what kind of crystal structure we will be formulating? And then you can just calculate their ionic ready, and you know, okay, it's 0.55. That's why we're going to formulate a octahedral, because it's right in between. All right. And this is also the same as, maybe you remember, the sodium chloride. Okay. I think that was something for you to practice what we have learned. And here I'm giving you another example right here. It's so-called rock salt structure. And this is the famous, let's say, sodium chloride microstructure or crystal structure. Basically, this is a octahedral structure. So now you can visualize even better if you didn't get it when I just showed you at that rather abstract picture. Here you can see it better. So this is basically the sodium cation, which is sitting right in the center. And then your octahedral is formulated by this 4 anions in the middle plane and 1 on top and 1 on the bottom, right? All right. So this is another example, or another 2 examples. So magnesium oxide and iron oxide. So they are exactly having the same structure as sodium chloride. All right. So here I'm trying to give you another example with qubit. So when we have a bigger ionic ready, so here where the example is given by what is it? Cesium chloride. So you see the cesium ion is really as big as the chloride, and the kind of ionic ready is almost 1, and that's why we're gonna kind of formulate a cubic structure. And here, maybe you notice, this is basically the AX crystal structure. So we have 1 equivalent anion corresponding to 1 equivalent cation. Yeah, I asked you that question already. So what is decisive for the number of cation to be seated into the anion structure? Maybe now you should get a sense of it, because the number is dictated by the neutrality. Yeah, for example, if we need to make sure we have a AX structure, meaning when we have the cubic structure of the anion here, yeah, basically in this unit cell we have only 1 equivalent anion, right? And that only allows us to sit 1 equivalent cation right inside. So this is also what it is possible to sit. But you see the cases that we're able to contain more cations in the unit cell, but we have to lose them because we have to make sure we need to get this kind of neutrality. I'll just show you some example right here. So when we have a AX2 crystal structure, so this is a material so-called fluorite. Yeah. For example, the first example here is the calcium fluoride, so which is corresponding. So 1 calcium cation is corresponding to so fluoride anions. So what will happen? The idea is simple. So you know the fluoride and calcium, they will kind of construct a cubic structure. So the crystal structure is cubic, that is clear. But for some reason, we're not forming a AX chemical formula, we are forming an AX2 formula. Yeah. And the reason, you know why? The reason is the neutrality. Yeah. So how the crystal structure will adapt to fulfill the second rule, which is neutrality rule. As you can see, the structure is still a cubic. Yeah, as you can imagine here. So we're putting not only 1 cubic here, actually we're putting 8. So 4 cubic structure top and 4 on the bottom. Yeah, I hope everybody realized that. And now we cannot afford basically always 1 cation into 1 cube. And that's why we have to go with a certain pattern. The pattern is in this 8 cubes, we will only have 4 cations. So meaning if you just look at this 2, the top corner, the top left corner, let's say, you're actually having your cations only in 1 of them, in 1 of the cube. And the other the kind of the right top row, you also have only one cation in one of the cube. The same applies to the bottom 4 cubes. So with this kind of pattern in total, you're gonna make sure your neutrality, because in 8 kind of cubes, you only have 4 cations. I hope that is clear for all of you. And actually, if you just look at this small cations, maybe you see we are formulating another kind of tetrahedron, right? That's why you see materials is always about tetrahedron, as it is repeating many places. So you have very good examples, or very many examples of such a AX2 either crystal structures, or let's say crystal structures together with the chemical formula. And here I'm giving you even more complex ones. So this is ABX3, so which is rather a mixture between, you know, anion and cations in a complicated way. You see here the anions are not just sitting for a FCC structure anymore. It is actually creating a FCC structure together with your kind of cations. So this atoms. So this is just for you to know. Yeah, we would have even more complicated structures when the chemical formula is becoming more complicated. The important knowledge for you to understand is about this AX structure, and you should be able to calculate what kind of crystal structure we will formulate according to the ionic ready, and how many kind of cations will be sitting in the interstitial places due to the neutrality for the AX kind of formula, right? All right, I think that's enough about the crystal structures. You learned enough about it. Now I'd like to give you a few examples. So basically 2. The first one is a family of silicate ceramics, and the second one is carbon. So for the first one about the silicate, and you probably should know this kind of structure, because we're talking about silicon and oxide. So for silicon and oxide, they, according to the ionic ready, the stable crystal structure will be a tetrahedron. So we have, you know, the silicon kind of cations sitting into 4 oxygen anions over there. And this kind of structure will be able to create many kind of periodic structures. So if you imagine this, if it goes with the FCC structure of oxygen, and you probably remember that will create a structure we just learned before, similar to the second example I gave you. So the zinc blend, right? And that is a structure that the silica has. Yeah, maybe you know that, right? So what is silica? Silica is your sand. Yeah, sand is a crystal. Maybe is some knowledge for you to realize. A very common sand is a crystal. But if you just rearrange your atom, because the basic structure here is about this tetrahedron. That is the stable structure. And we set for most of oxygen, they will go with FCC, but not all. So not all the oxygen anion will be sitting into an oxygen structure. They could be going with other structures like what you see here. Yeah. And that is a point I would like to introduce you. Maybe you learned this from your high school, right? So-called polymorphic forms. So you know the silica is a polymorphic form of quartz. And here I'm giving you another example, is so-called crystal baylite. Yeah. The difference, I mean, the common, first of all, the common thing is they're having exactly chemicals formula. This is something you know. And they even having exactly same crystal structure, which is this tetrahedron. What is different is how they kind of arrange the kind of repeating unit when you construct a bigger unit. unit cell. So this is how it looks like when you have a crystal baseline, and you probably could imagine the structure is also different for quartz. And you should know for all of them, they're so-called this polymorphic forms of silica. And due to this kind of basic unit, this kind of tetrahedra is having a ionic bonding, and that is explaining you why we could use the sand mode. Maybe remember when we talk about casting, the first casting methodology is sand casting, right? We told you the reason to be able to use sand is because sand is providing a very high melting temperature. Now you should be finally get the connection right here, because this ionic bonding between silica and oxygen is really providing you a rather high melting temperature. Yeah, so it's something around 1700. All right. So this is not just for sand; it is actually applying for all these polymorphic forms, because the unit cell, the crystal structure of this smallest unit is always the same. All right, and that brings up to a application of glass. So I'm not sure if you know how glass is made and what is the connection between glass and sand. Now, if you don't know before, I could tell you glass is just a form of sand. This is the interesting part about material science. So you could turn sand into glass. Of course, you could also turn sand into chips. Yeah. What is the difference? So glass, first of all, you should remember, is not just the material you see, the kind of glass you're having your water. Glass is also a structure. Yeah, it is a structure like crystal structure or non-crystal structure. So glass is a non-crystal structure, first of all. Yeah, and there are basically two forms to formulate glass. So the first one is just to fuse the silica. So pure silica, which is silicon oxide, and there's no purity over there. But silica itself is a crystal. If you just fuse it and make it non-crystalline, you're going to have glass. Yeah. And the second way to create glass is you still just heat it up and fuse it, but you also kind of add certain impurities. So the impurity could be sodium cation and calcium cation and so on. So here I'm giving you an example about this kind of soda glass. Maybe you heard about it. And the reason called soda glass is you're adding some sodium cations into this kind of non-crystalline silica, and then you're becoming a sodium glass. All right, that was about glass. I hope you finally get the connection between glass and ceramics. The second example I want to give you about ceramic is in terms of their structure is carbon. So here we're talking about the specific carbon. The first one is diamond. So everybody is familiar about this. So diamond is having actually a tetrahedra bonding between all the carbons. So this is something different from all the other, because here we don't have, let's say, cation anions. They're just the carbon elements. It's pure in a way. And the structure is tetrahedra, as you can see here. Maybe you also have learned this from your high school. And that is the hardest natural material known. Yeah, so actually not the hardest material existing in this world, because now we could build even harder material. For example, graphene, maybe you heard about it. The scientists who discovered graphene won the Nobel Prize 10 or 15 years ago. That is the hardest material. So I will talk about graphene in a second. And it has very high thermal conductivity. We're going to talk about thermal conductivity next week. If they kind of formulate into large single crystals, so we call them gemstones, right? Girls should be familiar with that. And if you just kind of create polycrystals, that's something we discussed before. We mainly use it to cut, to formulate tools. And it can also be foams to be coated onto some hard substrate. All right, that is about diamond. And the second carbon material, let's say, we're going to talk about is graphite. So that is the polymorphic forms of exactly carbon. But here we are not remaining the same structure. So you only know it is the same chemical formula in a way. But it is not tetrahedral anymore. Actually, it's a hexagonal structure in 2D, and then you just layer them into 3D, and then you become this so-called graphite. Maybe you were wondering what is graphene. So graphene is basically just one single layer of your graphite. Yeah, you basically break this kind of bonds over here. Maybe you know the bonds between the layers is the weak van der Waals bonds. That's why your graphite is rather soft. Yeah, it is a very good material for lubricant. But graphene, on the other hand, is very hard because the single layer is very hard. It has very high strength if you just pull it in plane, but if you can perform an indentation out of plane, that is worse than carbon. Worse than diamond. Yeah, so that also tells you the kind of hardness is a little bit different from strength. Yeah. All right, that's 2 examples. So now let's move forward to the final part about structure, which is about defects. Actually, this is rather something pretty simple. So first we start with point defects. As you see, for point defects, we have 2 types. One is vacancies, and the second is interstitials. Yeah, everybody should be pretty familiar with this stuff already. So it's just we could have now, cation and anions. They usually have different types of vacancies. It can be an anion vacancy. It can be also a cation vacancy. But usually for interstitials, because you remember cations are always much smaller than anions, so they tend to develop this kind of interstitials. Yeah, this is the unique feature about it. And then we also have 2 types of specific defects. One was called Frankel defects. It's nothing but a pair of vacancy and interstitial. So pair of, let's say, cation vacancy and interstitial. And we also have the Schottky kind of defects. This is just a pair of kind of vacancy of your anions. All right. The same equation is applied here. Maybe you still remember how to calculate the density of vacancies or the concentration of defects. This very famous form of equation, exponential form of temperature. Maybe you remember. When we go to absolute 0, what will happen? It's the same as metals. Okay. Here I'm giving you just a few examples or a little bit more knowledge when we just try to keep the try to have some foreigner atoms or foreign kind of cantals. For example, here we have the sodium chloride. That is the normal structure without impurity. But if we have some cation as impurity, we should remember we have to keep the neutrality. That means if the cation is becoming an interstitial at the place, it will at the same time create a vacancy at another place because we have to keep the neutrality. This is rather easy to imagine for you. And the same also applies for the substitutional anion impurity. So if we have a oxygen anions replacing a chloride anion, because this is with 2 minus and that has 1 minus. So if this impurity comes, it will at the same time create an anion vacancy. All right, I think everybody is in the sense of that. And that was all for crystal structure. And we talk about crystal structure itself, and we also talk about the defects. Yeah. So we didn't talk about dislocations and the slip planes and all this stuff, because that will be too long for today's lecture. But you could imagine similar things will be applied over there as well. Instead, I would like to show you what is looking like at the phase level. Actually, it is not so much different from, let's say, our metallic materials. So we were speaking about aluminum, copper, aluminum, zinc phase diagram, and iron carbon phase diagram. So for the ceramics, it's the same. So you have magnesium oxide and aluminum oxide diagram. So you see we have liquid solution, solid solution with these two components, and also mixture. So solid mixture and liquid solid mixture. Maybe you could recognize here it's somewhat a eutectic point. Yeah. All right, we will not go to details right here anymore. You just kind of keep in mind what you learned with the metals would be completely applicable when we speak about ceramics. All right, I think that's enough for all the structure level knowledge, and let's move forward to some property level knowledge and try to make you some connections between the structure of ceramics and the properties of ceramics. So the first property we're going to speak about is mechanical property. Yeah, you know the typical feature about mechanical property of ceramics is they're hard, but they're also brittle. Yeah, I don't think we explained you why they're brittle. Yeah, maybe you wonder. Ceramics are so much similar to metals. They have somewhat similar crystal structure, and they have somewhat, let's say, stronger atomic bonding. Why they're brittle? Yeah, and here I'm giving you a few reasons without very detailed or quantitative explanation, because we didn't learn them in detail, but you should get it as a concept. First of all, being brittle means they cannot go through plastic deformation, right? Because brittle means they're gonna break already at their elastic deformation regime. And why they cannot go to plastic deformation? Meaning what? Meaning they cannot do a lot of dislocation motions. This is something you really have to keep in mind. Plastic deformation is always connected to dislocation motions. Yeah, if you get very good, plastic deformation, meaning your dislocations are rather easy to move. If it's hard, meaning your dislocations are not that easy to move, right? And that means for our ceramics, their dislocations are hard to move. What is reason? So why they're difficult to move the dislocation in ceramics? The reasons are two, actually. The first one is ceramics have fewer slip systems. Maybe you could already imagine. So we have the BCC with something about 24 or even 48 slip systems, FCC kind of 12 slip systems. With this rather simple and symmetric structure, either pure FCC or BCC. So for ceramics, the structure is becoming a little bit more complex. And that's why the slip systems will be fewer. Yeah. I cannot show you because we really didn't show you all the slip systems, but you could imagine already by adding the cantons into the FCC anions, you're creating a complicated structure with fewer, let's say, slip systems. And the second reason is also very dominant is for metals, you can really easily move up and down or backward, forward, because there's nothing kind of so different, yeah, because the metal atoms are rather, uniform. But for our ceramics, it's a little bit challenging because you have a directional bonding. So the directional bonding means you have anions and cantons. So when you try to move, the anions to a similar charge, when you have a similar charge, they're going to develop, resistance, right? So when you want to move a kind of anions over another anions, that's going to be extremely difficult. Yeah, that's why it is hard really for the dislocations to move when we have ceramics. All right, so these two reasons hopefully are good enough for you to understand why the ceramics are brittle. Okay, and the second, let's say, property about ceramics is more specific for glass. And it is rather on a thermal property. This is something very interesting for you to realize, because there's even an unsolved problem we didn't emphasize before, and I would like to just give it to you because this is not solved scientifically up to today. It is not engineering materials, but it's a very common material. I will just tell you at the end. But first of all, let me show you what is our engineering materials behaving. So the idea about this property is thermal property, and it's related to somewhat thermal expansion, but not entirely. The first item or the kind of measure we would like to use for this property is so-called specific volume. So this is nothing but 1 over the density. You kind of realize what this is measuring, and this is measuring a specific volume, right? When you have the same mass of your materials, how much volume this material is going to take in space. As you could imagine, this is a temperature dependent measure. And here I show you what the crystalline materials will behave typically. So crystalline materials here we are referring to not only metals, but also ceramics. Yeah? For example, silica, yeah, calcium fluoride, and all this kind of materials. When there are crystalline materials, you will typically have a higher specific volume when they're in the liquid form, right? When you have the gas form, it's even bigger. So I think everybody could imagine. The reason is when you're having the liquid or solid gas form, your material is much more disordered, and you will have the browning kind of motion and so on. And so the specific volume is higher. And when you just cool it down, yeah, when you meet the melting temperature, when it becomes to solid, so becomes to a crystalline material, ordered material, the specific volume is becoming smaller. And if you just continues cool down, and this is the thermal expansion. Yeah, everybody get it? So when you just still cool down, your specific volume will become smaller as well. But there's a big jump between this kind of phase change in terms of specific volume. This is how the crystalline materials behave. But if you just think about the non-crystalline, for example, glass, what they behave, this actually also tells you how do we produce glass out of silica. Yeah, basically we're going to heat it up to a liquid form, and then you apply a supercooling. So the supercooling is in the extent that you're going to create a so-called supercooled liquid. So you will not have this jump in terms of specific volume, rather a kind of monotonic change, or even sometimes a linear change in terms of specific volume. And this kind of phase is still liquid, but it's a supercooled liquid. And until you reach a certain temperature, this temperature is so-called glass transition temperature, TG. Because at this time, you become solid, yeah, but it is not a crystallized solid. Yeah, so here you become sand. Yeah, if we talk about silica again. So here you become sand with a crystal structure. And if it develops into a non-crystalline microstructure, amorphous crystal structure, you become glass. Okay, and the reason for this is because the reason for the glass is being, let's say, transparent when you compare glass and sand. Actually, it is lying into the grain boundaries because it is not a crystal structure, and you will not have the grain boundaries. Yeah? And the grain boundaries are actually scattering the light. That's why you can see through when you have glass, and you cannot when you have silica. All right, I think now you know a little bit more about the connection between glass and sand, and also how all the crystal structures are behaving. I told you there's something that people cannot explain, which is also interesting. I mean, common sense tells us when you just cool down from liquid to solid, your specific volume will decrease. Yeah, everybody got it. Can someone give me an example? When you just cool down from liquid to solid, the spec volume increases. Now, this is beyond the scope of our course, but it is such a common thing you see. Let me ask some of you. I mean, anyone, maybe just gave some idea. Yeah, Alexandra, do you have any idea about it? Alexandra, are you speaking? If you're speaking, please unmute yourself. Let me ask Courtine. Courtine, do you have an idea? Now, it's a very simple material and a very common material.
No, sorry, I have no idea.
You have no idea? Take a guess. Let me ask. Who? Do you have an idea? Let's see how kind of creative you guys could be. William, so anyone. Can you give an example that for a material, when you cool it down from liquid to solid, your specific volume is expanding. So basically the volume is expanding instead of shrinking when you just go from liquid to solid. And I think this is the awesome. This is the reason. So who? Water is the guy. Yeah, that's right. Maybe this is the only example, the only exception. Yeah. And to be honest, the science that you have learned up to now and the science you haven't learned up to now cannot explain why water is going to a completely opposite. Because water to become ice, you know, ice is a crystal. Maybe you don't imagine, but ice is crystal. So when you just cool down your water from liquid to solid, it becomes ice, but the ice is bigger. Maybe you have the common sense if you just try to cook some ice on your own. And this is a mystery. Actually, there are many mysteries for water. The simplest material, well, let's call it material on this earth. You know, it comes as the earth was created or was kind of generated by what kind of theory. Water was there, and we don't fully understand it. Yeah. All right, so I think that was the perfect moment to add this course. You see, we are not done completely about material science engineering. It creates so many interesting unknowns in our basically knowledge seeking. All right, so let's just summarize what you learned for today. So today we said we're gonna expand your domain of knowledge. and from metal-driven kind of study to other materials. We focus on the structure primarily, and also connect a little bit to properties. The material we're expanding for you is ceramics, because that's, if not the second, if not the first, definitely second largest used engineering materials, or let's say just the materials in our daily life. And you know what is it, the definition of it, and you also know the types of it. I hope after today's lecture, you could really recognize what is ceramic, what is not, right? And you learn about the interatomic bonding of ceramic. This is something you know actually already. And what is more related for today is you learned there are two rules that decide the, let's say, crystal structure of ceramics. And the first one is the ionic Randy, and the second one is charge neutrality. So the first one decides where basically the cations are going to sit into your anodes unit cell, and the second one decides how many they're going to be able to sit. And then you also learned about the different imperfections. They're just given by name and rather easy to understand. Especially when you have impurities, what will be a little bit extra compared to the metals is you always need to think about the charge neutrality. That's the unique part. And finally, we kind of gave you a connection between the, rather an explanation why the ceramics materials are brittle. Everybody knows they're hard and they're having high stiffness and strength. Now you also know why they're brittle. And you also learned finally how glass is made and how it is different from sand. All right, I think that's all for today's main lecture. Just a few announcements. And the first one is maybe something you noticed. So next Monday is a national holiday, Independence Day. So we don't have lecture on Monday. Our lecture will begin on Tuesday. That is the last lecture with new knowledge, let's say, which is about expanding your knowledge domain from this time property side of you, because we were mainly focused on mechanical, or we learned systematically about mechanical. But you didn't really learn too much about thermal and electrical. So we're going to do that next Tuesday. And the second lecture is scheduled on Friday, but I would decide to give you a rather recorded lecture. And because Friday is pretty late, you will have exam right after a few days, right after the weekend, actually. So the recorded lecture will kind of help you with the kind of reviewing the study. And more importantly, the recorded lecture will not give you new knowledge. It will be a review lecture. So maybe you learned from Wenqi during the exercises, you could really write on the wall about your questions. So which part you don't fully understand and which part you need to get, let's say, a refreshment from my side. So I would rather to address those issues. And of course, I will give you some personal advices or connections of all the concepts that we learned for this lecture. This will be provided as a record, and it should be available latest before the exercise session next week. So the exercise session next week is still at the same time. It will address you some questions that appeared during your assignment, and more importantly, it will give some information about exam. So be there, don't miss it. Yeah, the rest is something you know. The reading chapter in the book is 11, 12. So 11 is processes, 12 is about ceramics. If you want to learn more about ceramics, you could definitely go to 13, 14. And if you want to learn more about polymers and composites, you could go 15 and 16. But they will not be considered into our scope of study, and you will not meet them in your exam either. All right. I think that's all for today. If you have any questions, it is time. Otherwise, I would see you next week. All right. That sounds good. So enjoy the week, guys, and see you next week. So see you, Rufei. Bye-bye.
Thank you. See you.
Bye.